All right, so let's go over the types of radioactive decay. We've already talked about alpha and beta, and there's a few more that I want you to know. So there are 6 common types of radioactive decay. Alpha emission, or alpha particles, again abbreviated with the alpha symbol. It kind of looks like this. Or you can write it like this, the helium. So it is the emission of a helium nucleus, no electrons, but 2 protons, 2 neutrons, which is an alpha particle. And so it is knocked out of the nucleus of an unstable nucleus, and an alpha particle gets shot out. And so, of course, what's left over inside will have 2 protons less and 2 neutrons less. 2 fewer neutrons, 2 fewer protons. So here's an example of a radioactive decay of alpha particle. You can see here, so radium-226, if it loses an alpha particle, it loses 2 protons, so the new product will have 86 protons. It loses 2 neutrons, total mass of 4, so 4 plus 222 is 226. So the product that is left over after the alpha particle leaves is radon-222. So 2 fewer protons and 2 fewer neutrons. So a total of 4 nuclides less in the numerator. I'm sorry, in the superscript. Like I said, you can write, if you write an alpha particle with the 2 and 4, that's just as good as helium. Okay, the beta emission, which we've already talked about, again, abbreviated with the beta symbol. Sometimes you'll see the negative sign to differentiate it from a beta positron. But anyway, a beta particle is really like a high-speed electron. So it's not an electron that's in the electron area, but it's coming straight out of the nucleus. And so once the electron leaves, what happens, this is literally what happens, a neutron converts itself to a proton, and because a proton is positive and a neutron is neutral, what it has to do is emit a negative charge. So an electron gets emitted. So a neutron converts to a proton, and a beta particle or an electron gets shot out. And this is also energy. So that's the radiation that's coming out from it. So here's the actual conversion. A neutron converts to a proton. And you can see that, again, even in this case, they add up. So a proton plus a beta particle plus 1 and -1 equals 0, and 0 plus 1 is 1. And so this is the conversion of a neutron to a proton, and a beta particle is emitted. So notice that the number of protons increases. The total nuclides don't change, because if a neutron converts to a proton, then the mass stays the same. And so the mass doesn't change, but the number of protons does. Here's an example of the beta decay of carbon-14. The particle is a -1, beta -1, 0, or again, you could write it with an electron. So you can see that, you can actually see it. We've got 6 protons here, and to make this balanced on the right-hand side, this has to be 7. And so we actually have increased the number of protons from 6 to 7, but since the mass number has stayed the same, now we have 7 neutrons. So here we had 6 protons and 8 neutrons, and here we have 7 protons and 7 neutrons. So we've actually converted a neutron to a proton, and a beta particle is emitted. Positron is exactly the opposite of a beta emission. So a positron emission, a positron is a particle that's the size of an electron, however it is positively charged, and it in fact converts a proton to a neutron, and in the process it emits a positively charged particle, a positron particle, and again radiation. So here's the process that so it's the equivalent of taking a proton and making a neutron. Notice that again they add up. So a proton has 1 proton and 1 total protons and neutrons. A neutron has 0 protons and 1 total protons and neutrons. And a positron then, so this is kind of an oddball because it obviously doesn't have a proton, but it's a positive particle that is shot out. So that we write the 1 there so that we can balance out our nuclide symbols. Here's a radioactive decay of technetium-95. This is an example of a positron emission. So here you see technetium has 43 protons and 95 total protons and neutrons. If a positron is given off, then what's left over is 42. 42 plus 1 is 43. So the new element only has 42 protons. And notice that the total mass has not changed again. And so here we have 43 protons and 52 neutrons, and here we have 42 protons and 53 neutrons. So we have converted a proton to a neutron. Electron capture is a little bit different. It is the decay of a nucleus. A nucleus is unstable, and instead of giving off something, what happens is it actually, so this one actually does it takes an electron from the closest electron, grabs it, pulls it into the nucleus, and then what happens there is it leaves a little hole right here. And so what happens next is other electrons from higher up levels come down because they want to get to lower energy. So as they come down, they give off energy. So there's like a what do you call that? A waterfall of electrons kind of falling toward the center. So is very similar to a positron emission, but it's kind of in the opposite. In this case, notice here's my arrow. In this case, the proton is still a proton converts to a neutron, but in this case, it grabs an electron. So that's back to negative. So it grabs an electron, and now a proton plus an electron gives you a neutron. And so it's still converting a proton to a neutron, but remember the beta particle was like this, went to a neutron plus a positron. So a positron converts a proton to a neutron and gives off a positron particle. In this case, this grabs, it captures an electron, that's why it's called electron capture, and converts a proton to a neutron. So slightly different. They tend to be one or the other. They kind of go hand in hand, or kind of predict. If you need to convert a proton to a neutron, both of those can work. An example is potassium-40. So potassium-40, if it grabs an electron from the inner electron, it will become argon-40. And so, like I said, the energy is not from the actual capture, but from the other electrons falling down to the lower levels and then giving off that energy as that happens. One other, we talked about gamma emission. Gamma emission tends to be, is not a particle at all. It's actually just energy. It's emission from an excited nucleus. It sends out a photon, which is really like light. It corresponds to a wavelength of about 10 to the minus 12 meters. So it's a little bit smaller than an X-ray, but so it's sort of like that. So it's very, very dangerous, and but it's not an actual particle. It's just energy. A lot of times what happens is a radioactive decay produces this metastable excited state, and then it just gives off the energy to kind of come back down. So so we probably won't have too many of these equations, but here's an example. Technetium, the M just means metastable. It's not really stable. And so notice that the nuclide doesn't change at all, but it just gives off a gamma particle. So these are not as interesting to write out anyway. One other that I want you to know is fission, spontaneous fission. Fission would be when an unstable nucleus breaks apart into two lighter nuclei, but notice that they're not like an alpha particle or a beta particle. There's actually more protons and neutrons than so it does actually, the big one breaks down into two smaller ones, and oftentimes neutrons are given off. And energy is also released. So you'll know it's fission if all your products are smaller nuclides. So here's an example. So uranium-236 decays under fission, and you can see that one of the products is yttrium-39 and iodine-53, or iodine-136, yttrium-96, 39 protons, 53 protons, and then four neutrons. I do want to note that if you see a coefficient here, make sure and count them all. So notice in my total, this is 96 plus 136 plus 4 times 1, so 4 gives you 40, gives you the 236. So notice that there's 4 of those. Of course, the 0, it doesn't matter. So on the bottom, we've got 39 plus 53 is 92. I will tell you that you can't really, you wouldn't be able to predict what it breaks apart into. So if this were a kind of reaction that I wanted you to fill out, I would like leave one of these blank. You know, like I might leave that one blank and have you figure out what it is. So you would know. I don't think I wouldn't be able to for sure predict how, because it might break down in different ways. This just happens to be one of the ways. But anyway, just so you realize that. But you can identify it as fission when you've got 2 bigger particles. So this is just a summary, what an alpha particle is, beta, positron. Electron capture actually gives off X-rays, but that's just because it's captured an electron. So here's the process. So like I said, beta converts a neutron to a proton, positron converts a proton to a neutron, electron capture also converts a proton to a neutron, but in a different process. You can see the changes in mass number, the changes in atomic number. Some don't change at all, some go down by 1, up by 1, down by 2, so forth. So this is a handy little table. So like I said, it's the nuclides that are outside the band of stability that tend to be radioactive. And I sort of mentioned this earlier, things that are to the left of the band have more neutrons than what they need, and so they want to try to convert neutrons to protons. So they tend to decay by beta emission, so they want to reduce the neutron to proton ratio. They're trying to get rid of neutrons, so they tend to decay by beta emission. Nuclides to the right of the band of stability tend to have too many protons, and so they want to convert protons to neutrons. So they will tend to either decay by positron emission or electron capture. And at this point, you wouldn't be able to tell which one. So if I asked you, which one will this go by, you could say, well, either positron or electron capture, because they kind of go hand in hand. And then it turns out the very heavy elements, especially those with atomic numbers greater than 83, generally decay by alpha emission, although they can decay by beta emission as well. So we'll see later that we tend to have a series, and so there can be others, but if they're greater than 83, they tend to at least decay by alpha, at least one decay by alpha emission. So here's again the summary. So to the left, beta emission, to the right, electron capture and positron emission, and then above 80, where is it, 83, above here tends to be alpha emission. So everything above here tends to be unstable. That's the end of my stability there at 83. In a minute, I'll show you. So what we're going to do is we're going to look at what is the stable. So like, you know, with 60 protons, this one right here has about 86 neutrons, and that has to be stable. So what we can do is we can compare if we have one that has 60 protons and way more oh yes, if we have 60 protons and way fewer neutrons, wait a second, the other way. If we have this many, it's this way. If we have 86 neutrons and way fewer protons, then we need more protons, so that's when we undergo beta emission. If we had 60 way more protons for 86 neutrons, if we had too many protons to the right, then we have to convert to neutrons. And so anyway, this is how I'll show you an example in a minute. So let's predict the expected radioactive decay for each of the following radioactive nuclides. So what we're going to do, I'll do calcium-47 first. The best way to do it is just to compare to what the average is, the average atomic weight. So the average atomic weight for calcium is 40. So that kind of tells you that the most common isotope, this is not an exact method, but it's what we're going to do. It's as much as we're going to do. So it's like we expect calcium-40 to be very stable. And so what's here, if we compare this number, so this means that for this calcium has way too many neutrons. 7 is way bigger than 40, and the number of protons obviously can't change because it's calcium. So this means it has way too many neutrons. It has more neutrons than it should have. So that means it's to the left. If you look at if you go to 20 and then go up to the band of stability, which would be 40, 20 and 40, and then this 47 is kind of over here. So it's to the left of the band of stability, so we will undergo beta emission. It wants to convert neutrons to protons, so beta emission wants to get rid of those neutrons. What about aluminum? So this is kind of the opposite. If you compare, again, aluminum-25, the atomic average, the average mass is 27, so this one has too few neutrons. It needs to convert some protons to neutrons, so it's going to undergo either positron emission or electron capture. And again, I would just write both. It's going to be one or the other. And then, like I said, if it's above 83, then usually you can predict alpha emission. A lot of times, something is unstable, will become something else unstable, and so it goes through a sequence of radioactive decays. So one thing will decay to a second thing, which is also radioactive, which then decays to a third nuclide, and so forth, until it finally lands on a stable nucleus. A lot of times, they end up landing on a stable isotope of lead. So some of the radioactive decay series found naturally out in nature is uranium-238 tends to decay a bunch, uranium-235, and thorium-232. So I think the next slide shows some of that. So here's uranium-238. So this is what a radiation series is. So you start with uranium-238, and it's gonna give up an alpha particle to become thorium-234. Well, that actually is not stable either, so it undergoes beta emission to give me Pa, which I'm not sure what that is, and then gets back to uranium-234. Well, that's not really very stable either, so it undergoes alpha. What is that? It should be 2. And I don't know what that means. Okay, well, this should be thorium, TH, and this should be 230 because it's uranium has 92. Uranium has 92 protons, so it will lose 2 protons to become thorium, and if it's 234, it's going to lose a total of 4 neutrons, so it's going to become 230. So that should be TH230, and then it loses another alpha particle. You can see it going, then some betas, and some of these series kind of overlap each other, but they tend to end up like with some kind of stable lead. Certainly, this is not something you have to memorize, or I would expect you to recreate. Just understand this. The idea that lots of times there's a radioactive decay series, so they'll go through a number of radioactive reactions until it gets to something stable.